Hello. Hello, good afternoon, and welcome to this session. I think it's time that we start the session. Otherwise, we're going to miss some important presentations. So, my name is Vasilis Baousis, and together with...
My name is Tina.
Yeah, and we're going to actually facilitate this session. We have 6 nice presentations that will be presented by the respective presenters. And we start with the first one, that is from Gabriele. First of all, I would like to apologize for misspelling some names, but this is happening, sorry. And he's going to talk about challenges and opportunities in the adoption of high-performance computing for Earth observation application in the Exascale era. So the floor is yours. Just for the speakers, you have 10 minutes for your presentation and 5 minutes for the questions. We have 6 presentations, and we have to stick to this so that we don't miss the opportunity for the remaining presenters to present their work. Thank you.
Thank you very much. Thank you very much for the introduction. I'm very happy to be here and actually honored to open this session on high-performance computing. So, computing technologies and industry have undergone tremendous changes in the past decades. So initially, Moore's law propelled the semiconductor industry to pack an ever-increasing number of transistors and logic into the same space. Then the end of the nanoscaling marked the limits on how much we could reduce voltage and current without compromising predictability. Then the instruction level parallelism wall made the start of the multi-core era. However, as the number of cores increased, new challenges with energy efficiency and thermal management emerged. We also encounter limits in parallelization due to Adam's law and not enough general purpose application that can be parallelized. So we are now in the race of new trends aiming to optimize performance cost energy equation for specific tasks. So performance trends in supercomputers were directly related to those in the microprocessor industry. So here you see performance of the world's fastest supercomputer from the pre-computer era to today. We measure computing performance using floating points operation per second, FLOPS. Since 1993, top 500 project has been ranking supercomputers utilizing high-performance linked-path benchmarks. A significant milestone was reached in the first teraflop computer in 1997, followed by the first petaflop supercomputer in 2008. With the ending of Dennard scaling, computing performance has continued to grow exponentially, just at a different rate. So when did we move from pectascale to exascale computing? Well, the first supercomputer to achieve 1 exaflop was Frontier in 2022, operated at the Oak Ridge National Laboratory. This was achieved 4 years later than anticipated. The reason is that exascale computing regime, there are many challenges that we have to face: concurrency, energy efficiency, memory storage, and communication. As a reminder, exascale computing refers to the capability of perform a billion operations per second. But what is actually a supercomputer? Well, it is a high-performance computing system that includes a high number of processors, vast amount of memory, and more importantly, a high-speed interconnect network with low latency. The network is the feature that differentiates supercomputers from cluster of computers, cloud computing, high-throughput computing. HPC have been adopting more and more accelerators to boost computational performance. GPUs have become the main choice due to their parallel processing capabilities. Until now, NVIDIA has been the dominant player. Nevertheless, other vendors will gain more space. GPU in HPC is at the basis for accelerating artificial intelligence applications. Indeed, artificial intelligence is a driver of compute trends. Since the release of AlphaGo in 2015, we have entered the era of large-scale deep learning. It is a phase characterized by significantly higher computational requirements compared to other models published in the same years. Indeed, there has been a huge rise of large language models. They become fundamental technologies in the field of natural language processing. They are transforming the way we interact with analyzed text-based data, and most importantly, they have demonstrated remarkable capabilities, which will have for sure economic implications. Big tech companies have been announcing their supercomputer for some time already. This means that supercomputing has evolved beyond traditional scientific computing, which was primarily driven by large governments. For example, Tesla has been working on developing its custom supercomputer to process the vast amount of data generated by their vehicle sensor and for making real-time driving decisions. But what about Earth observation and remote sensing? Well, Earth observation has been and continues to drive disruptive computing technology. And here I want to take it from the very beginning with an example of SAR. In the early 1960s, SAR posed a significant big data challenge. By the late 70s, SAR had become one of the primary applications of supercomputers. For example, in 1985, it was presented an evaluation for implementing a SAR processor on the Cray-1 supercomputer. On this very messy slide, I just want to show you that HPC and parallel computing have been adopted to tackle a wide variety of remote sensing applications, even before AI. This includes interband registration, mosaic image correction, dimensionality reduction methods, lossing compression, generation of large products. HPC will serve one of the primary computing platforms for the Destination Earth project. This is clear. Destination Earth, in fact, intend to connect HPC and cloud-based solutions with several Euro HPC sites using different architecture and ecosystems. But let's consider briefly AI foundation models, which is kind of now the current keyword that we hear a lot. Well, we are just at the beginning in developing foundation models for Earth observation. For example, let's consider the model PRIVNI developed by NASA and IBM. Here, I just want to highlight two aspects. Firstly, there is a large gap in the size of the models and performance when compared to large language models. In EO, we still have a lot to do. Secondly, to train models like GPT on cloud costs a lot. For example, more than 1 million if you consider a typical subscription in AWS. Let me remind you here that supercomputers operated by the Euro HPC can access for free if you just write a proposal, which will be then reviewed by peers, reviewers. So, as we've seen previously, computing industry has gone through several decades of evolution, and computing performance has increased by order of magnitudes. Current and future trends will continue to push computing beyond current limits. And this messy slide again show again what could be the probable trends that we're going to encounter and have right now. But for now, let's just focus on some. Modern supercomputers are becoming increasingly heterogeneous. These affect all components of the system, from the processing units to the memory hierarchies and the network components to the storage system. At the Hewlett Supercomputing Center, we have coordinating the project DEEP EU-funded project that has been driven the development of modular supercomputing architecture. This architecture is a computing environment that integrates heterogeneous systems, HPC systems. It is modularized by the software stack and enables using different types of computing technologies to serve a large range of applications. For example, data analytics, simulation, and deep learning. JC is already implementing MSA in our production system, Jewels and Eureka. So I will briefly show you an example of an application that can benefit from MSA. For example, here we have XPIC. It's a particle in cell simulation code from the University of K11, used for forecast space weather events. The workflow has two parts: a particle solver to calculate motion of charged particles in electromagnetic fields, and the field solver to compute electromagnetic field evolution. So these two codes have different natures. The particle solver has limited code scalability, frequent global communication, while the field solver has highly parallel with billions of particles and the long-term, long-range communication. So with this kind of system, it is possible to match the processing of the most suitable hardware. And by doing this, you can gain performance of 1.8 when compared to just computing on the single partition module. So Exascale in Europe will be largely based on modular supercomputing. Here I show you the perspective that we have at the EULIS Supercomputing Center. We started in 2011 with the EU project DEEP, which got more than 120 million euro for funding. We went to the project then Software for Exascale Architecture, funded by the Euro Joint Undertaking project. Then we had the pre-Exascale machine. We have Lumi, CXC Finland, we have Leonardo, Cineca, Italy. We have Mare Nostrum 5, Barcelona Supercomputing Center, Spain. Then we have other projects currently running, the European Pilot for Exascale, OPEX, and High Performance and Quantum Simulator Hybrid, the HPC QPC-QS project. But from 2024, we can expect the first Exascale SPC in Europe. So EuroHPC will fund 50% of this project, of this supercomputer, while the remaining will be funded by by the German Federal Minister of Education and Research, BMBF, and by the Ministry of Culture and Science of the North Rhine-Westphalia. Jupiter will be implementing a dynamic modular supercomputing architecture. It will include high scalable booster module and a general purpose cluster. And here I want to highlight that the cluster module will be based on CPER's Neuria processor made in Europe, a CPU with high memory bandwidth developed in the framework of the European Processor Initiative. And the booster module will have NVIDIA GPUs. So more information for this supercomputer will be actually announced next week at the Supercomputing Conference. And with this, I would like to stop here, hopefully on time. And I usually this opportunity to thank all my students, my colleagues at the EULIS Supercomputing Center, and project and collaborators. Thanks a lot.
We have some time for questions. Anyone would like to ask a question to Gabriele? Thank you very much.
If anyone doesn't have a question, maybe you can explain us more about this European CPUs.
Okay, what do you want to know?
Is it based on ARM?
Yes. Yes. So it's a new architecture, of course. I mean, we are, of course, waiting, right? We know that. It's taking more time. Of course, it's a new challenge for Europe to invest and produce this kind of architecture. But of course, there is a lot on the plate, right, for this technology. Not only so OPEX, the first scale pilot that we're developing in the project OPEX. We have then, of course, Jupiter, which will include in the partition this kind of processors, and then, of course, new probably supercomputers. Very important for energy efficiency, right? So, but yeah, I'm not sure I can tell you more on that.
Thank you. So there's one question behind.
Hello. I was wondering, in the remote sensing world, we are much concerned about data and how much data can be close to our processing. How do you see that in data transfer, in getting the data if we want to use those machines?
Yeah, this is the question of $1 million, right? So where the data are. It is clear that we will have to find synergies, especially in the domain, for example, of destination Earth, right? So you have to find a way to make sure that the data are moved as less as possible. And if you see in the scheme that I showed you before for the platform for destination Earth, it is seen that HPC will play a role as, a place where you do some computation, right? The question there is how much and what actually data will be processed at that part, right? So there is no way to escape this part. So either there is a huge investment, like in this one, where everything will be in a place, right? Data, the computation. Otherwise, this will always be a challenge. And yeah.
Thank you.
Thank you very much. So we have no more time. So if you have any question, don't hesitate to go and say him in the coffee time. And thank you very much.
Thank you.
So let's move on to our next speaker, Ben Hal Rammel. Yes, thank you. So he's going to show us his work on enabling global scale Sentinel-1 time series analysis through streaming.
Thanks for the introduction. Hi, I'm Bernhard. I'm a university assistant at the remote sensing group at the TU Wien. I actually started out, I have a background in software engineering, specifically in high-performance software. I've been writing for the video games industry and also computer vision applications later on. And now I'm back at TU Wien, and I'm going to introduce you to the methodology that we developed to create a high-resolution soil moisture map using Sentinel-1 data. So first, why did we create this map, actually? Well, we wanted to find out backscatter anomalies that kind of interfere with our soil moisture retrievals, such as subsurface scattering. And I'll talk about this in a moment. But first, why is soil moisture data so important? Well, actually, it is a core component of many applications, from digital twins, like here from DG hydrology, or for drought monitoring, as we see here an example from ESA. But also, we heard today in the introduction lecture already from the GHG KIT project, where the data is used for numerical modeling of greenhouse gas emissions. So yeah, it's many applications. So what are those anomalies we're talking about? Well, subsurface scattering, well, usually what we assume is that there is a linear relationship between microwave backscatter and soil moisture, which means that if microwave backscatter gets brighter, we assume that the soil got moister. However, over certain areas, especially arid regions, this relationship can be inverted. It's because the top soil layer becomes more and more transparent, and we start seeing what lies beneath. And if we have strong scatterers beneath the topsoil layer, the more dry the topsoil layer gets, the more transparent it becomes, and the brighter the signal gets, which is exactly the opposite of our assumption. So how do we find that? Well, because you have this negative linear relationship, then you could find it maybe if you relate the microwave backscatter with some reference soil moisture data and calculate the temporal correlation. And then the idea is that if there's a strong negative correlation, that's when subsurface scattering occurs. That's exactly what we did. We aligned some reference soil moisture data with the high-resolution Sentinel-1 data, developed an efficient process to handle this data volume, and finally also we minimized the orbit effects, but I'm going to focus in this talk mostly on the high-performance implications. So the first challenge was aligning or resampling our reference soil moisture data, for which we chose the ERA5 land reanalysis soil moisture model data, which is provided by ECMWF at a 9-kilometer resolution. And we have to resample or realign this with our Sentinel-1 raster data. And to do that, you need a lookup table. And to create a lookup table, you need a spatial index, like a KD tree. But because of the large images and the high resolution, kind of has a very significant demand on your memory. So we create this lookup table in chunks. Luckily for us, the open source PyResample package already does that for us. However, when we developed the method, we exposed some performance bottlenecks. So the first rule in high-performance software engineering is before you do anything or program anything, you should measure. That's exactly what we did. We used the PySpy sampling profiler to actually look at our alignment and resampling code. And already you can see here that about 90% of the time we spend concatenating those lookup table chunks onto each other, which results in lots of length copies because we extend this array. So what can we do about this? Well, actually, once you know where the problem is through the profiler, it's quite simple. We already know how big the lookup table is, so we pre-allocate the array and reduce our alignment from half an hour to roughly 4 minutes. And with the help of the very nice community from PyTroll and PyResample, we also integrated this now in the official package, and this performance benefit should be available in the latest releases. So now we have our data aligned and everything's there. Now we need to process it. And to kind of, because we have such a large data volume, we need a high throughput, so we actually finish in a normal time. And the first method is to get high throughput is to use streaming. So what is streaming? Well, in a nutshell is you exploit that certain operations are inherently single-threaded, like reading from the disk, decompression, these things. And you kind of read a chunk of data and decompress it, and then use the processes that are easily parallelizable, use the other cores to do the processing of the parallelizable data. And while you do the processing, you already fetch the next chunk of data. Of course, this only works really efficiently if the fetching of the data and the processing of the data take roughly the same amount of time, or at least that the fetching is somewhat faster than the processing. So now you must know that our Sentinel-1 data lies around as a stack of geotiffs. So if we would go the straightforward way and just read out the tiny time slice from it and then do our correlation processing on it, it would actually take a long time to fetch it because we have to open thousands of files to read out tiny slices and construct our time slice. That's why we developed this iterative correlation method, which is based on Welford's algorithm to calculate the variance and the co-moment. And with that, we only have to keep track of some running quantities, like the running mean or the running sum squared of differences to the mean and the co-moment. And this actually updating this quantity takes roughly as long as reading a geotiff file. And with that, we are able to achieve a throughput about 1.7 gigabytes per second. And this allows us to calculate the 5-year data cube in about 2 hours on a standard VCF4, the Vienna Scientific Cluster node. I'm sorry, there's a mistake on my slide that I just noticed. It's 48, not 64 physical CPUs on a standard VSC4 node. And also the RAM usage is quite reduced. So now let's quickly talk about the orbit effects. As you can see from this nice animation from ESA, Sentinel-1 is not covering the Earth in a homogeneous fashion, and it also looks at the Earth from various angles. And because of that, it actually introduces some form of bias into the data, as we can see here in figure B, which dampens the correlation effect. So we want to remove this bias, and we just did this by calculating the correlation coefficient for each orbit individually, and then calculate the average weighted by the number of observations. And that's seen in figure C. This kind of removes this bias and gives a much stronger correlation signal. So now I want to show some results. Well, first, we calculated over the arid regions of Somalia, where we looked at aerial images and some soil groups. And you can see here that the soil sensitivity map and some of the soil groups, they nicely match up. And there is also, we want to do future studies where we want to deeper investigate this relationship between this correlation coefficient and the subscatter and the soil properties. But speaking of future studies, already Professor Wagner submitted a manuscript where we looked into more depth into the Sentinel-1 based soil moisture sensitivity map. Specifically, we processed now the data of a much larger region, namely the Iberian Peninsula and parts of Northern Africa. Coincidentally, this is also the same study region we used where we did similar things with the ASCAT data. And we kind of, if we relate those two data sets next to each other, you kind of can see that the overall patterns, luckily for us, seem to match. So what do we want to do in the future? Well, first, currently, the whole streaming process I talked about in the start is currently hand-rolled. So we wrote this manually in Python, but we want to move this fully to Dask so we can utilize the Dask framework more better, and it would also give us the possibility to use the Dask gateway, which will be implemented by UDC, and I think Christoph Reimer on Thursday will have a more detailed talk on it. Otherwise, I guess you can hit them up at their booth at UDC if you want to know details. And of course, we want to roll this out globally and actually develop a method of validating this huge high-resolution data set. And I mentioned it in the beginning already. We also want to use it to improve our existing soil moisture retrieval products now that we have it. And of course, there are some nice options that we could investigate as well, like the algorithm. It's very easy to adapt it to calculate, for instance, seasonal soil moisture sensitivity maps, or to port the whole thing to better improve the throughput even further and make it even more cost effective, port the whole thing to GPU and let it run on GPU hardware. And yeah, with that, I reach my end. I thank you all very much for your attention. And also thank all my collaborators and all the open source communities listed here that helped in the development of the project. Thank you.
Thank you very much. Any questions?
Thank you for a nice talk. Could you explain in a bit more detail the pre-allocation step that you talked about in the first slides?
Yeah, sure. So here, yeah, this bottleneck, it's, oh, I don't see it. Anyway, I can explain it also like when we created this, there it is. When we created this lookup table chunkwise in the back of the, because in Pyro sample, the application, it was never this high resolution, so it never really came up. But when you do with NumPy or like any continuous memory vector, you add up tiny chunks onto a large vector. It has to first, before adding this tiny chunk, create a new slightly larger vector, copy the large vector into the slightly large vector, and then copy the chunk at the end of the vector. And you do this every time you add another chunk at the end, which kind of gives a lot of mem copies, and this can up like significantly. And this was a difference between 30 minutes and 4 minutes in that case. And by pre-allocating this once, we got rid of the problem. Thanks.
May I? Yep. Thank you for the very interesting presentation. Just one question. So your analysis, as far as understood, managed to, let's say, have in parallel the data fetching and the data processing in a way that you can optimize the overall process. Mm-hmm. The question that I make is based on your experience. Do you expect that the bottleneck in the future, given the hardware change and, let's say, the software evolution, will be on data fetching or in data processing?
That's an excellent question. It's actually one of the considerations we made for deciding for this algorithm as well, is because in the future we expect to have actually also temporarily more observations. So it depends if the data fetching or the processing becomes longer or shorter, depends again on the algorithm and on the resolution changes. If in the traditional way, the slice we could cut out, the time slice would become narrower and narrower because the data would get longer and longer, and that means the fetching would also take longer and longer. So we would have this dependency on time. But with this iterative approach, it's constant in time. It doesn't matter how many, at least for the increase in fetching, because of course there is a linear increase because I have more time to process. But let's say, for instance, my resolution significantly changes for Sentinel data. Like let's say 1 meter, like insanely. It's easier for me to chunk up then in a special way and reduce the memory and the fetching again than going the time-based way, especially if it's stored like in these spatially aligned data structures. It would be different if in the future we would have temporally aligned data structures. But because you get observations each day in, it's actually for data providers a nice solution to just store them spatially aligned. Thank you.
Yeah. Yes. Okay. Very quick one, please.
Are you interested in calculating higher order cumulants beyond correlations, especially for multivariate series?
Yes.
I have algorithm for that. That was the fastest, at least sometimes some years ago. So we can talk later if you want.
Yes, we actually, that's for the future what we plan, especially when we talk about soil properties and things. The multivariate is very much on our minds, yes.
Okay, thank you. We have to move on to the next presentation. We run out. Thank you. Thank you. So the next presentation from Martin Jussi. Sorry again for misspelling. It's advancing GPU accelerated SAR processing technology and tooling. The floor is yours. Thank you.
Right. Hello, everyone. Good to see all of you. I'm Martin Jussi from CGI, and I'll tell you about advances in GPU-accelerated SAR processing. So essentially, how to achieve processing in the order of petaflops without owning a supercomputer. So today, we'll talk about a bit of the background, and actually I would very much like to thank Gabriele for the first presentation, because he did half of the job for me and also already explained most of what I wanted to explain in much more detail than I have time for, so I will not stop too much on that. Then I'll talk about ALUS Toolbox, our software we've developed in CGI Estonia for GPU-accelerated EO data processing. Some performance figures and some new developments and opportunities enabled by our approach. So GPUs, graphical processing units you heard about, traditionally being used for video rendering and gaming, but more contemporarily much for AI model training, but also for cryptocurrency mining and a lot of general computational tasks. So GPUs enable massive parallelization capabilities. And here I have one figure about the trends, but the key message here is that the GPU compute capability advancements have been kind of exponential over the past years, as opposed to CPUs, which have still been kind of linear. And why is this important? Is because of this. So at the same time, in the Earth observation, you could also see that the data growth is kind of exponential, and also in the next years to come with the new missions flying, we will have a lot more data produced, which we somehow need to process, and with the purely with the CPU power, it will not just be sufficient. So to tackle that problem in a way, we've developed a little toolbox called ALUS. It's an open source toolset for accelerating EO data processing using GPUs. It's open source, it's free to use. You can check out the GitHub repository. There's a link here, but also a QR code later in the presentation. And it's mainly been developed in cooperation with ESA, so there are a total of 5 ESA activities where this has been either as under development or used as part of the solution. So how we've developed these tools, from the very beginning we've taken a kind of a community involvement approach. So we've involved various Earth observation experts from a number of different organizations, some of them might even be in this room right now, to understand how they use mainly SAR data, which algorithms they use, and moreover, we would go into small details on how they use the particular processing tools in SNAP, so I'll tell you about that a bit later. So the input to our developments have come from the EO community and been supported by a number of different users. So what we've developed as an output of this conversation are GPU-enabled processing tools or routines. For those of you who use the SNAP toolbox, some of these terms may sound very familiar to you. So essentially, we've asked these users, okay, so which EO algorithms, which SAR algorithms you use, and moreover, show us in the SNAP toolbox which exact tools you're using, which parameters you're changing, which of them can be hard-coded. So tell us in detail what you're doing, and what we try to do is to develop similar tools, but implementing the GPU infrastructure to enable massive acceleration of the same tools. And these are the tools that we've developed. So we have a coherence estimation routine for generating coherence imagery, a calibration routine for producing geocoded Sentinel-1 SLC or GRD imagery, a more sophisticated coherence routine for timeline generation, a resampling routine that works on SAR data but also optical, a very generic one, and some SAW focusing ones that I'll also tell you and show you a bit afterwards. So for the SNAP users, these figures should also, especially the left one should also be pretty familiar. So this describes our coherence routines. So the one on the left is a generic coherence pair generation routine, all GPU enabled. And the one on the right is just a bit more sophisticated version with improved caching and user experience mechanism for generating a long coherence time series. So you can have 2 or 10 or 100 inputs to this routine. You can generate a coherence timeline using GPUs. While we develop, we always do accuracy assessment against the SNAP toolbox. So we use the same algorithms in SNAP as kind of a ground reference data, so to say. So we would compare our results to the same results from the SNAP toolbox. And this figure is particularly for the coherence estimation routine. The differences are highlighted in the colors. You can see that the differences are different across the scene, but they're still very, very small. So we're talking about pixels per million. So 10 to 100 pixels per million is the relative error. So it's a very small difference when compared to what the SNAP produces. So the outputs are perfectly usable also for scientific work. This is the Sentinel-1 calibration routine. I'm not going to stop too much here. Also very standard for SNAP, but all GPU enabled. And you can see here that the accuracy of this one is even a lot higher. So we've kind of made the zero differences transparent. Otherwise, this figure would just be all black. But you can see that there are some differences in between our result and the SNAP result highlighted in blue, but still very diminutive. So the toolbox has GPU-enabled routines. It uses hardware based on availability. So if you have a GPU that you can actually partition, you can run multiple instances of our software on the GPU. So for example, if one instance of the software doesn't use all the memory that your GPU has, it would just use part of it. You could run 3 instances on one GPU. So if you have 10 GPUs, you could run 30 instances, which is pretty good for massive parallel processing. And you could also provide your inputs on multiple levels. So full scenes, sub-SWAT level, single Sentinel-1 bursts, or an AOI. And we are also supporting SRTM and the Copernicus DEM, so you can do global processing. The toolbox has an emphasis on pure processing, so just a command line interface. So any other analysis needs to be done by external tools. So you just need a processing environment with a Linux, GPUs available, and the data, your data, and you can do the processing. We have some Docker images available on the GitHub repository for you to ease the use. And here's also an example of the command line input. So you specify your scenes, your output directory, your AOI, and your auxiliary files, and you're ready to process. We've also recently done some SAW focusing work. So under an ESA TDE activity called BULP, we worked together with SAMAP, CGI Italy, and the University Polytechnic of Bucharest. And we developed a prototype processor for ALOS pulsar zero Doppler focusing. We achieved nearly interactive performance. I'll show you a figure later. So this has a huge potential to develop into a serious on-the-fly processor. It's supporting different modes, and it's using the range Doppler focusing algorithm. The processing performance we achieved was very, very high. So the total runtime of the processor is around 1.7 seconds. And around 0.4 seconds, there is just calculations on the GPU. All the rest goes to basically file I/O, so reading the data into the GPUs and writing the outputs. So very, very fast processing. And to build on that work, we've now started cooperation with the ESA QA for EO team service led by Telespazio Vega UK. So Esrin are looking into renewing their on-the-fly processors. And as part of our work, we are building GPU-enabled NVSAT ASAR and ERS-SAR processors. So these kind of processes would potentially be a game changer for accessing any heritage data and performing any reprocessing campaigns, because you can do the SAR focusing in sub-second level. And we've released the NVSAT IMS mode already, and we'll release another mode in November. So this is also an open source project available on GitHub, which you can have a look at. And now, if you can do your processing that fast, then we have enabled a kind of a new concept to do the end-to-end processing really from level 0. So if you can generate any products in seconds or milliseconds, then why would you store level 1 or level 2 at all if you need a level 3 product in the end? So you could always generate your end products, be it level 1, level 2, level 3, always from level 0. You wouldn't have to store your intermediate products, so you could save on storage costs, but also you would never have to do any reprocessing campaigns because you would always be processing your level 0 data with the latest processor. So this is a concept we believe that could really fly in the next years. And to demonstrate this, we have a very short demo, only lasts for seconds, I promise you. So we will now process 18 seconds of raw SAS signal from NVSAT ASAR to a level 2 terrain-corrected product using a ranged Doppler terrain correction algorithm and an SRTM3 DEM. So here we go. It's just a quick demonstration. And there you have your outputs on QGIS. So if we go back here, very quick, this is actually the last slide, so I'm not going to waste more of your time. But you can see that for SAR focusing, the range compression took around 117 milliseconds. The azimuth compression took around 244 milliseconds. And the terrain correction took around 100 milliseconds. So it's very, very fast. And if you want to add any processors there, it's probably just going to increase the total time by 1 or 2 seconds. So thank you very much for your attention, and I'm open to any questions.
I think that we run out of time. We are not going to take any questions, and we proceed to the next presentation. So you can have any questions related later on.
So now we are with Artur Milowski, and he will talk about quantum machine learning for remote sensing, exploring potential and challenges. Go for it.
Thank you very much. My name is Artur Miroszewski, and together with my collaborators, we've prepared a short presentation about quantum machine learning for remote sensing. And instead of giving you a very specialistic talk devoted mostly to quantum specialists, we've decided to take a step back and prepare a little bit more general talk about, well, giving the update of how the field looks like right now, what are the challenges, and what's the potential up, well, to this day, let's say. Okay, so let's start. So what is quantum machine learning? I believe it's quite a new field that probably quantum machine learning has no precise definition yet, but it encompasses at least one of those 3 points that I've listed here. Either it's classical machine learning, but which is inspired by quantum mechanics. I believe this approach is slightly on the side of the mainstream. There's also a performing full quantum algorithm on a quantum computer, but in most cases, I believe this is still a far future. Therefore, I will focus on this during this seminar on hybrid classical quantum machine learning algorithms. In this case, those will be the gate-based devices, in which we utilize the interaction between the classical device and the quantum device. Gabriel already mentioned some of that in his talk, that the architecture is being developed on that. And so in this approach, machine learning task is divided into the parts which are performed on a quantum device and parts which are performed on a classical device. Two examples, the most well-known examples, are quantum neural networks, where the cost function is computed on the quantum machine, but the gradients to teach the network are usually done on the classical device. Closer to my heart, kernel machines with kernelized supervector machine, when the whole procedure is done on the classical machine of the SVM procedure, but the input kernel is estimated on the quantum device. When the field kicked off, okay, so people believed that there are some characteristics of quantum machines that allow us to perform some tasks better or to obtain a quantum advantage. And in this case, I will call quantum advantage as for QML is having a better machine learning performance, for example, better classification accuracy than any classical counterpart or any state-of-the-art classical algorithm, and also not being able to simulate the quantum algorithm efficiently on a classical machine. And right now, the field of QML in remote sensing is quite actively explored. There's the literature on that topic is growing. The architectures are being proposed. Lots of those are actually done in collaboration with ESA. So everything looks very nice. So it's time to talk about the challenges. A short comment on the hardware. So maybe not all, but we can see lots of those projections, how quantum devices grow. And well, honestly, that looks fantastic. Lots of qubits soon, hopefully. But there's one catch. Well, the qubit number is not all, okay? And if we want to have a fully functional quantum computer, we have to care also about other aspects like qubit quality or qubit connectivity and other things, which I guess that, for example, connectivity seems to be bigger problem than the size of qubits. So just to, this is a comment for you to be a little bit more skeptical of giving one number to a quantum device and believing that it will solve all the problems. Software-wise, there are some challenges to be alleviated. And well, there are lots of beautiful results about the algorithm execution on quantum device, giving, for example, exponential speedups on quantum device. But lots of those results, very nice results, somehow skip the part of the state preparation from which we start the algorithm, or the measurement. I will talk about the measurement in a minute, but the state preparation quite commonly can need exponential number of gates. And somehow the bottleneck is not in the algorithm execution, but in the state preparation. Some authors say that, well, we can initialize the state from some kind of quantum memory, but honestly, no such thing exists yet, so I will not bet on that. The other aspect, which is extremely interesting, is the untrainability issue. So when we have a neural networks, we would like to teach this neural network, right? And it is done by optimizing the cost function. When the landscape is nice, we can initialize our neural network somewhere, compute gradients, and in a finite number of steps, we'll reach global extremum. Well, it seems that it's not always the case for quantum neural networks. It seems that the characteristics where the quantum machines were supposed to be the strongest, they also lead to some problems. And it has been observed that the landscape for quantum neural networks tends to become completely flat, which means that when we randomly initialize the neural network, we basically cannot find the correct gradient, and we will not find the global extremum, and well, we may not be able to teach the neural network. The very same problem, maybe not the same, but very similar problem we encounter in kernel methods. When we compute quantum kernels, we observe kernel concentration, which means that as we increase, for example, the size of the machine, the independent kernel matrix entries tend to, for fidelity kernels, vanish exponentially fast. So basically, we end up with almost identity matrix, which, well, we don't need quantum computer to initialize identity matrix. Okay, I like to look at this problem as we have a distinct group of people which are distinct. We would like to distinguish between them, but as we increase the size of the quantum machine, their faces get more and more blurred, and well, we have a problem to actually identify who is who. Okay, so the final note about the challenges is the quantum state measurement. So the computation with quantum computers is done on the quantum state, to which we actually don't have a direct access. We have to measure the state, and it's always a probabilistic measurement, which in most cases means that if you would like to have more precisely estimated result, well, we actually have to perform more and more measurements. We have to repeat the circuit many times. And, well, I just told you about the problem of distinguishing the results from the quantum computer, right? Which means that they get exponentially close to each other. So distinguishing between them would need an exponential number of measurements to actually be able to say something about it. Okay, and it seems to be quite a big bottleneck in quantum machine learning. We've run a very simple, maybe simplistic analysis that, well, okay, we don't have a exponential speedup, but, well, let's not hope for this separation of complexity classes. Maybe, well, we'll have any speedup. And it seems that, yeah, we cannot dream for exponential speedups, well, in those cases, but the speedups are still achievable, at least for some sizes of the machines. So maybe I'll not go through conclusions, but rather I would like to answer a question, which will be probably my take-home message. So is quantum machine learning a low-hanging fruit? And honestly, I can answer, no, it's not a low-hanging fruit. Some maybe founding fathers of the field thought that it's a low-hanging fruit, but as we explore it, it seems that it is a fruit, okay? We are maybe not sure yet what kind of fruit it is. Maybe it's a quantum superposition of fruits, or maybe actually it's a completely new fruit that we'll have to still discover. We find some challenges. I guess we are able to go around them, but we have really to understand what we are doing to utilize the possible advantage of quantum computing. And, well, the field is quite new. Lots of results are being done, and lots of no-go and go theorems are being produced. And, well, I hope that this fruit, probably not as sweet as we initially thought, well, I think it's still probably pretty tasty and worth discovering. Thank you very much. Cool.
Thank you very much. Any questions?
Thank you.
Yeah, thank you very much for the honest talk, I guess. I feel like what you've showed for QML is like generic enough to be extended to any usage of quantum computers, right? I mean, what is the specificity here? And should we have the same worries about quantum computers in general, that the gain might be not as big as we expected?
Yeah, well, so I would say that, can I have the, oh, thank you. I would say that lots of these challenges that I mentioned are quite general for quantum computing, okay? Maybe except this untrainability, which seems to be really focused on the machine learning tasks, so cost function optimization or the finding kernel machines, right? The initial idea to use quantum computing for that is that there are some classes of functions that can be estimated exponentially faster on the quantum device comparing to the classical device. And well, I hope, well, I think that this is still true, but yeah, so those two issues, the untrainability and from the untrainability, the problem with the measurement seem to be quite focused on the quantum machine learning. The other are rather general, right? And where they, you can basically apply them to the whole field of the quantum computing.
Thank you.
Probably there will be some person who object and say, no, I have a very good algorithm that does not have those things, but okay, no one, great.
Hi.
Hi.
I heard in your presentation that the accuracy of the classification increased to use quantum machine learning. I heard that at some point. So focus on hybrid methods as kernel supervector machines that you say that the only was a hybrid method that you use the quantum machines in order to create the kernels. I asking and thinking about what is happening with the quantum machines in that case, because I thought that increase the potential of the data and decrease the timing of the processing. But I think that at the end, the functions of the kernel are equal in both cases, in the classic and quantum. Can you provide a little bit more of information of that, please?
Could you repeat just the last few?
Yes, you say that the accuracy increased in the classification, and for instance, you say that supervector machines is created a kernel in the quantum machine, but the rest of the model is in a classical machine.
Okay.
So I would like to know if there is any change in the functions to calculate the kernel on that case.
Yeah, I mean, the initial hopes that I think are still present for using, for example, quantum computers for kernel machines was to utilize the first thing, the exponentially big Hilbert space in which the functions are estimated, okay, which can lead to increased, well, maybe not accuracy yet, but expressibility of our model. Secondly, it's well, the idea is that using quantum entanglement can provide us some insight of the internal correlations between the data. And the initial thought was and still is, I believe, to use at least those two aspects of quantum machines to hopefully increase the accuracy of the machine learning methods that we have right now, the classical ones. Although I believe that, yeah, the field is still quite new, and the challenges I've told you, I've presented to you are rather are rather robust, but I can already see people going around those kind of challenges. So we'll see what happens next. But well, the hopes are still quite high, okay? And I believe that using both quantum kernels, for example, or quantum neural networks can give a benefit for those kind of tasks.
Thank you.
Thank you.
Thank you very much. So let's thank the speaker and let's go to the next question. So the next speaker is Guillaume Passelot, and he will show us about his work on quantum contrastive learning for semantic segmentation of remote sensing images.
Okay. So I will present some work on behalf of my colleague about quantum contrastive learning methods for semantic segmentation. And I would like to thank the previous author for his inspiring introduction on quantum computing. So a bit of context. So it has been written many times, but still, today we have large volume of data, but in some cases, we mislabeled data to do a proper job. And in this context, we are looking at methods that are weakly supervised or even self-supervised that could help. And in the recent days, contrastive learning methods have gained popularity because they are self-supervised and they have been successfully applied in various domains. So in the frame of a study funded by CNES, QC4Geo, our goal was to assess the impact of quantum computing on Earth observation classification problems, and more specifically on the weakly supervised problems. So the strategy for this work was to investigate an hybrid method with the addition of a quantum layer in a contrastive learning framework. So to do that, we started from work done by Jaderberg et al. And we compared this hybrid method with a kind of simple PCA method that is supposed to give us a kind of blind representation of the data, and also to a classical CNN method to perform semantic segmentation. The input data for this experiment was made of Pléiade images on Toulouse and Montpellier. So here I will describe a bit more in detail what is this contrastive learning framework. The main idea is that in a scene we take a patch and then we select another patch that is slightly shifted from it. So that would be this one. Taking the assumption that these two patches have the same content. And we also select another patch that is distant here as a kind of negative example. We process these three patches through a CNN encoder. So here we go from, let's say, in our study, we had 11 by 11 RGB batches. So we get, after the CNN encoder, to a state vector of size 8. And after that, we give this state vector, this kind of intermediate representation, to a quantum layer that will try to enhance and transform this representation. And in the output, we have we have a state vector of size 4, and in the end we have the triplet loss that we are trying to optimize to have the for the contrastive approach. So this is for the training part. So we do the training on a set of patches, and then after, when we have trained both the CNN encoder and the quantum layer, which has some parameters inside, for any patch we can generate an intermediate representation of size 4, and taking all this representation using a sliding window, we can do unsupervised classification. For instance, here we used k-means to have to identify the different clusters inside this representation space. So here a bit of detail on the quantum part. So we reused a circuit that was done by previous work from Kong et al. Because it was a circuit kind of simulating a quantum convolutional network, and we adapted it to an 8-qubit for this work. So the implementation was done using Penny for the quantum part, and using the training with the hybrid training using PyTorch on a set of more than 2,000 patches. And so the results that we get, so we see that the CNN and the hybrid method perform significantly better than the simple PCA method. But still, we see that the CNN approach still has the best overall accuracy, and the hybrid method has a comparable accuracy. Just to mention, we had also ground truth data for some of the patches, so we have been able to compute this F1 score. And yeah, as a conclusion, the performance of this hybrid approach is still close to the classic CNN network, but it's not outperforming it. We have concluded that we have a possible lack of input data in this experiment to achieve better results, because self-supervised methods tend to require a significant amount of data. But here, for practical reasons, we had problems running it on a larger amount of patches in a reasonable amount of time. The future work that we expect would be to extend the dataset made for this experiment, but also to investigate computation on real hardware that will pose other challenges, because at the moment this experiment was only a simulation. And thank you for your attention.
Thank you very much. Does anyone have any question?
Hello. Hello. Yeah. So first of all, thank you for the presentation. So I'm not in the field. I'm not sure if this is a mean question, but so the talk before talked about the flattening of the landscape and so basically non-convergence of a training algorithm when set up with quantum machine learning. Why don't you see this? I got from the last few sentences that it's a simulation. Do you think it's a problem of correspondence of the simulation and reality, or is it a different kind of problem, or I don't know if you can.
No, yeah, what I meant by the lack of input data to do the training was really just the fact to run the training on a larger amount of patches to have more diversity, and in our test we have not been we have not been in the situation where the loss is just staggering and is constant. We still achieved training correctly, but the results were not in terms of maybe the variety of the patches was not as good as expected.
So the previous talk was mentioned, so well, I have to stand up then. Maybe it was quite a small neural network, right?
Yeah.
So as I said, well, the problem becomes more serious as you increase the size of the machines. In here, well, that's my guess. Just my guess that maybe the neural network was still a little bit, well, quite a small machine learning architecture. Okay, so well, if you increase the size of it, it will maybe get flat, but for small neural networks, you have a chance that those kind of things are not that visible. Is it correct?
Yeah, true. We did this experiment on purpose on a small circuit to kind of have a good understanding of what we were doing and try to tune the things. Of course, we are not expecting to achieve the best results that maybe larger CNN could get. Yeah.
Just maybe help me, my collaborator here. Barren plateaus are a problem in generic quantum neural networks, but there exists quantum neural network where this problem does not appear. So when you know what you're doing and when you look at the experiment a lot, you can find neural networks that work pretty well and can be trained pretty efficiently. It was just a comment, sorry.
Thank you. Is there any other question? If not, I have one more curiosity question. So which infrastructure did you really use to make this test?
To do this, well, you can use standard GPU to do the whole training.
Yeah, but for this simulation for the quantum computing
Yeah,
part.
it's on GPU
Okay.
also.
Okay, thank you.
Okay, thank you very much. Thank you. And we have the last presentation from Edward Jones on the application of neuromorphic processor. I've lost the neuromorphic application, so I have to use my processors and artificial intelligence satellite communications.
Okay, hello everyone. So I'm going to recount here a little bit of some work that was done, funded by ESA, and a collaboration between me at the University of Manchester and my colleagues there, and the Polytechnic University of Madrid and Thales as well. So to give you a little bit of context, I'm going to explain a bit about what neuromorphic computing is, maybe give you a little bit of a flavor of that, and kind of explain why this is a potentially useful technology in space. So you can see on the left-hand side here, we've got a typical sort of model of the von Neumann architecture. This is where you have lots of memory. you have lots of compute, and there is a bottleneck between the two. You have to move things in and out of your processor very quickly. Memory bandwidth is still a limitation, though, for that. And so what neuromorphic computing tries to do is design computational systems, hardware especially, that mirrors the sort of design or the evolution of the human brain. Right, so this is small computational units like neurons that have a broad connectivity between them. And typically they deal with very sparse inputs, sparse in time and in space. So these very sparse binary spaces are the kind of thing that we're exploring. And so linking this to AI and to deep learning as well, deep learning is made up of artificial neural networks. Artificial neural networks transfer typically floating point values between each neuron. Moving that towards a more biologically plausible model, we want to be communicating between our neurons using spikes. And that way we can actually take advantage of this neuromorphic hardware paradigm. The potential advantages here are for significantly lower power consumption or power usage for these models. So taking AI from something that is generally trained in a data center, maybe even inference run in a data center, down to being able to be done on device with very low power footprint. The human brain, for instance, approximately uses 20 watts and can do all of the things that the brain can do. It would be nice to have a little slice of that kind of power consumption for our algorithms. Another side of this is improved fault tolerance. Now, the adult human brain loses a neuron at approximately 1 every second, and yet we don't suffer the same kind of problems that you would see if you were to remove transistors from a typical von Neumann architecture at the same rate. There are significant challenges here. The encoding of data, in a similar way to the encoding of data in the quantum system, the encoding of data, how you use the spikes that are available to you is a problem. And also the sort of development of the platforms and frameworks that are available to support the development of neuromorphic algorithms. So there's two sides to it. There's the hardware and the algorithms. And as a sort of example, in the project that I'm describing here, we compared two platforms. We've got the Versal AI core series, which is an FPGA, a field programmable gate array. This is very, very low-level configurable hardware. And Spinnaker. Spinnaker is the neuromorphic platform in this case, and the Versal is the more traditional platform. And just as a kind of way of comparing these things on a number of different tasks. So the Spinnaker board there you can see, just to give it a bit more context, each of those chips on that 48-node board has 18 ARM cores on it. And it differs from typical high-performance computing systems by being relatively low power, but focusing on having many small, not very complicated computing units that have are very highly interconnected and run at quite low power. And so going to the sort of applications, what we tried out using neuromorphic computing on, there were 4 main tasks. And so we've got interference detection and jamming classification, which are both about identifying disturbances in satellite communication signals. In the case of interference detection, that is just seeing whether there is some natural interference. In jamming classification, it's identifying deliberate interference. And then there are 2 more, congestion forecasting. This is a time series type task where we looked at how we can predict when radio links would be particularly busy, and that could be used to mitigate that kind of thing, or change when things were transmitted. And also looked at pre-coding matrix computation, and this is sort of a beam-forming application to stop interference between transmitters in the same place. So those are the applications. Now, these are SATCOM applications, but neuromorphic computing is applicable to a wide range of different machine learning tasks, including sort of image processing especially. So just to sort of give you a background on the Versal, this, as I said, it's got some specific matrix multiply accelerators on it, but is quite flexible. And this is the example, as I say, of a non-neuromorphic platform. This has quite a substantial software infrastructure associated with it that allows you to quantize neural networks, optimize them, and compile them right down to the hardware. To sort of contrast that to what we did with Spinnaker, the neuromorphic platform, the tools aren't quite so developed, but we do have this a methodology for converting artificial neural networks, sort of deep learning models, to spiking networks. This has some issues with it, such as there are some unpleasant features that we have to deal with just to sort of make this model work, but it is built upon existing tools. And just to give sort of a sample of the results here, on the left-hand side you can see the throughput here. Now the throughput is significantly higher on the Versal. This is because the spiking neural networks have to represent, in this case, in a rate-coded model, the spiking neural networks running on Spinnaker have to represent values over time using a rate, and so there is a sort of an upper limit to that. Looking at the power consumption for the platforms, you can see there that Spinnaker is significantly lower. And so this provides some sense that, yes, you might have lower throughput, but you can do it at significantly lower energy consumption in terms of watts. So a sort of conclusion from this was that Spinnaker suits the kind of missions where energy is relatively scarce. These are typically things like CubeSats, low Earth orbit satellites, whereas the Versal would be probably potentially better in other applications where power was less of a concern. So this was just looking at Spinnaker 1. Spinnaker 2 is now in production, and Spinnaker 2 has a lot of features that are quite desirable relative to Spinnaker 1, including the fact that it's made on FDOSI technology, which is inherently radiation hardened, and because radiation is quite a concern in this kind of environment. Building atop that, there's also error-correcting memories that could be included in this, and the capacity to run multiple things in parallel, multiple programs, multiple workflows in parallel on the same chip would allow to compensate for any potential errors that might be incorporated there. But the real area where I think that there will be the most sort of progress in the future is to look at the coding, going beyond rate coding, going beyond sort of temporal coding into something that's a little bit more complex. So yes, just to conclude, Spinnaker would be quite suitable to be used on a satellite that is sort of energy constrained at the edge, as it were, whereas Versal sort of suits places where higher power is available. Spinnaker 2 is relatively flexible and it has potential for radiation hardening. But the real place where I think the biggest improvement will be seen is in the algorithms, in how we use spikes in spiking neural networks. Emerging technologies could also be a solution here. We're also involved in the Convolve and Nimble projects that are looking at making processors that can do tasks such as convolutional neural networks in very low power. So thank you very much, and I'll happily take your questions.
In the 90s, there were companies producing FPGA. That was programmable logic, and Xilinx was one of the companies, Altera, Xilinx, and I think that they prepared some logical programming. So it was a basic AND or NAND functions, and you were able to make quite big programs. So Even I was working in robotics, and for robot controllers, they use the FPGA. And it's like an FPGA 30 years later, no?
So yes, there are two different pieces of hardware here. Yes, the Xilinx FPGA is very useful. It's very adaptable. Yes, you're right. It's basically you can take your logic gates and put them and use them as you wish. The thing with the neuromorphic hardware is that it sort of sits somewhere between conventional computing and this very low-level configurability. So you've got something that structurally, in terms of the hardware, is fixed, right? So the connectivity there, although it allows lots of connectivity, Spinnaker's not very good at passing large amounts of data between those cores, but it can pass very small messages to lots of places. And so that's kind of what Spinnaker's optimized for. Now, yes, the FPGA was used there just as a kind of a contrast, and I think that's quite a good finding, is that FPGAs are probably a good thing to use in these higher energy environments at the moment, because they do have that reconfigurability. And if you've got something in space, you don't want to, you want it to be as reconfigurable as possible. But there is a place there for neuromorphic computing, and especially with improved algorithms that can really take down the amount of data that you have to transfer from the satellite to the ground, then I think there are significant power savings and opening up of new opportunities as well. But that's both with FPGAs and neuromorphic hardware. Yeah.
Hi, I was just wondering whether you were trying to use any kind of these asynchronous spiky neural network systems, like Loihi, for example, because here I understand everything is synchronous and basically digital. It is far from proper neuromorphic, like it is still very, very far from
Yes,
neuromorphic.
yes. It's not like the brain in the fact that there is a global time signal that synchronizes everything, but locally it is asynchronous actually. So it's globally synchronous, locally asynchronous. But yes, you're right. Spinnaker is a research platform, and it's designed to sort of sit in that halfway house between sort of analog neuromorphics and mixed signal neuromorphics, which bake in a lot of the algorithm sort of assumptions, and something that's a bit more general purpose. So you might say that it's a mixture of both. But yes, this is really what you want. You want it to be like Loihi and be asynchronous. But then there are assumptions that have been made in the design of Loihi that mean that there are certain things you can do on Spinnaker that you can't do on Loihi, for instance. So it's sort of, if you've got something in space, you might want to have that little extra amount of flexibility because the algorithms are still trying to sort of catch up with the hardware that's available.
Okay, thanks.
Hello, thank you for your very interesting talk. You mentioned the radiation hardening on your hardware. Why did you not use magnetic RAM for the memory, but ECC instead?
So, sorry, can you repeat the question?
In terms of radiation hardening, why did you not use magnetic RAM instead of ECC?
Yes, well, so this is very much a sort of future work. Yes, magnetic RAM might be a useful technology to employ in future deployments of this, but we haven't actually looked at the potential for the errors at the moment. We haven't done a sort of full fault analysis of it, but we do hope that sort of moving towards having algorithms that are matched very closely by the hardware means that you can have more errors without having to worry about things like radiation flipping bits in different places. But yes, there is still this. I think this comes down to the previous question: is that there is still quite a lot of abstraction between what's going on here and what's going on at the hardware level and what's going on in terms of the models. And so once we kind of get that nailed down, then we can say, okay, now this is where we really care about errors in our memory, and these places we don't. But yes, yeah, if we were to be flying this tomorrow, we'd probably look in that direction, definitely, yeah.
Okay, thank you.
Thank you very much. So now it's time. So let's thank the speaker. Let's thank them all, and thank you everybody for participating in this session.